learners, BME 025 Condition Monitoring and Maintenance Management. Video number 16, Maintenance Models 2, presented by myself, Dr. N. Venkateshwarlu, Professor, Mechanical Engineering, School of Engineering and Technology, IGNOU, New Delhi. Methods of total time on test plotting. So TTT plotting. The technique of TTT plotting, originally suggested by Barlow and Campo 1975, is very simple to use for machines failure data analysis. Like other probability methods, this method is also based on assumptions that the time between failures are independently and identically distributed, so that the actual chronological ordering of the TBFs can be ignored. Thus, it is not useful in analyzing a data set which have structures and are positive to serial correlation tests. The theory of TTT plotting. Suppose that 0 is equal to T0 less than T1 less than T2 up to less than Tn is ordered sample of times to failure of a unit, then the TTT is given by SI is equal to sigma I is equal to 1 to j n minus I plus 1 into Ti minus Ti minus 1. Thus S0 is equal to 0 and S1 is equal to N1, S2 is equal to N dot T1 plus N minus 1 into T2 minus T1, that is equal to S1 plus N minus 1 into T2 minus T1. S3 is equal to S2 plus N minus 2 into T3 minus T2, and Si is equal to N dot T1 plus N minus 1 into T2 minus T1 up to N minus 1, N minus I plus 1 into Ti minus Ti minus 1. Denote that sum or total time on test TTT at Ti I is equal to 1, 2, 3, 4 up to n. The TTT plot is obtained by plotting I by n comma ui for I is equal to 0, 1, 2, 3 up to n, where ui is equal to Si by Sn on a unit square and connecting the plotted points by the line segments. If the plot is concave downwards, the machine is deteriorating, and if the plot is concave upwards, then the machine is improving, and if the plot wriggles around the diagonal many times, the machine is experiencing failure rate. The maximum likelihood estimate, this is most popularly used term in reliability studies, in which the probability of the sample is obtained by multiplying the density function evaluated at each data point. The product containing the data points and the unknown parameter is called the likelihood function. By finding the values of parameter that maximizes this expression, we make the set of data observed more likely. In other words, we choose parameter values that are more consistent with our data by maximizing the likelihood of the sample. Thus, the MLE method is equivalent to maximizing the equation of several variables. If the assumption of independently and identically distributed is not contradicted for time between failures, the MLE method provides fairly good estimate of the parameter of the theoretical distribution. This method requires computer programs to do the calculation efficiently and rapidly. Further, there are some more methods available in literature for plotting TTT transforms, such as Kaplan-Meier expression or product limit estimates, piecewise exponential estimates, etc. TTT transform. The concept of TTT plots was provided to be very useful tool in many reliability applications such as model identification, aging properties, age replacement policies, etc. Plotting data is the first step to understand the information contained in the data. In case of failure data of repairable equipment, these plots indicate increasing or decreasing or constant failure rates. The health monitoring of any equipment can be found by using these plots, whether the failure data satisfies IID assumptions or not. If the data confirms IID assumption and the increasing failure rate, then optimal age replacement interval is obtained by plotting the scaled TTT with cumulative distribution function. If the data shows any trend in the form of deterioration or optimum replacement interval is obtained from the TTT plot by considering age of equipment as discussed by the Barla. The ratio of cost of failure maintenance to cost of repair maintenance is the deciding factor, that is known as a cost ratio. TTT plots can be constructed using different methods like Kaplan-Meier estimate, rank adjustment method, Nelson, piecewise exponential estimate, and maximum likelihood estimate methods. While first four methods are non-parametric, the last method is parametric. It is observed that whether the data is censored or not and follow IID assumption. TTT plots are more suitable when maintenance policies are evaluated. Sometimes it is necessary to clean the data when it contains inappropriate and misleading events before synthesizing it into a model to be used for future decisions and policy. The application of TTT transforms were advocated by Kelvjo 1982-1986, Kelvjos and Westberg 1990. From the shape of the plot, one can easily know about the failure rate of the equipment. By knowing the shape only, we can able to understand the failure rate of that equipment or the machine. If the plot shows convex upwards, then the machine is deteriorating, increase in failure rate, and if it is concave downwards, the machine is improving or decreasing in failure rate with time. If the plot crosses the diagonal several times, then the machine experiences a constant failure rate. That is, TTT plots can be drawn using several methods, namely maximum likelihood estimate, piecewise exponential estimate, and Kaplan-Meier estimate. The expressions are as follows. Consider an equipment with a CDF of Ft. Let 0 is equal to T0 less than or equal to T1 less than or equal to T2 less than or equal to up to Tn are ordered samples of times of failure events of size n from a cumulative life distribution Ft with F0 is equal to 0 and survival function Rt is equal to 1 minus Ft. Then finite mean is given by the ith TTT transform is defined as mu0 is equal to integral 0 to infinity Rt dt with minimum value of mu0 0 is equal to 0 and maximum value mu0 infinity is equal to mu. The scaled TTT transform is defined as TTT is equal to 0 to integral 0 to Ti Rt dt. Phi Ti is equal to integral 0 to Ti Rt dt divided by mu0. The curve between phi t and ft from 0 to 1 1 is the TTT transform, and it is the graphical representation of the analytical solution for parametric models. This transform is independent of scale. Thus, total time on test SI can be defined as SI is equal to n integral 0 to Ti r Ti dt, where S0 is equal to 0, R0 is equal to 1 and I is equal to 1, 2, 3 up to n. Expression for Sn is given by Sn is equal to n integral 0 to Tn r Ti dt. The scaled TTT phi I is equal to Si by n and CDF f is equal to 1 minus r. TTT plot is obtained by plotting phi I with Fi. So TTT plots. It is a plot of line segments joined between two successive discrete points. These points of scaled TTT and unreliability CDF are obtained from the failure data. It gives a picture of failure data in a plot of unit square. If the plot is concave or convex above or below the diagonal line, increasing failure rate can be inferred. When curve embraces diagonal line, the constant failure rate can be assumed. Let T1, T2 up to Tn be the n failure times of an equipment with suspensions between too few successive failure times. If all the units are put into test at the same time, total test time TTTI for all units at time Ti is defined as TTTI is equal to Ti, that is equal to sigma I is equal to T2I into n minus j minus 1 into Tj minus Ti minus 1, which is equivalent to the cumulative time up to the end of Ti for I is equal to 1, 2 up to n, where T0 is equal to 0. This is shown pictorially in figure 8.2. The plot of CDF, which is equal to I by n versus normalized TTT value TTT I by TTT n is the TTT plot. So this is the plot, TTT plot. This is also known as total time on test calculation. When the sample size n increases to infinity, the TTT plot converges to a life distribution Ft from which the sample has come, and it is the TTT transform. If Tn is not the last observed failure, then a pseudo time or last censored time after last failure Tn plus 1 is defined as TTT n plus 1 is equal to TTT n plus integral n to infinity RT dt, and the scaled TTT is phi I into TTT I by TTT n plus 1. So the following section show different methods of constructing TTT plots of censored or uncensored data. One is KME method. Many times it is not possible to observe failure times on test. The time for these items failures are not observed are said to be censored, but amount of time it is observed functioning is noted. In this method, the reliability RT at failure time Ti is given by RTI is equal to phi 1 to I into 1 minus d by n. So where n is the number of risk at time Ti and d is the number of failure time, it is common to regard Ti as an observed failure time even if that is not the actual situation. The total time on test is given by equation 8.28. The scaled TTT is evaluated and plot is drawn for observed failure times only. Thus the survival function is RTI is equal to n minus 1 by n, and TTT is referred to as SI is equal to sigma j is equal to 1 to I into n minus j plus 1 into Ti minus Tj minus 1. So thus the scaled TTT 5 is equal to sigma Si by Sn and F is equal to I by n. Next method, that is PEXE method. The distribution function called piecewise exponential estimator was proposed by Kitchen 1980 in the data of size n if T1, T2 up to Ti are observed failure times and Ti1 and Ti2 up to Tim are suspended data between two successive failure times, then the failure rate estimate is given by. In this method, constant failure rate is fitted to each interval. The exponential survival function are pieced together to form piecewise exponential estimator. This is a continuous function. In order to construct the TTT plot from PEXE, an estimate of survival function after time Tn must be made. If there are suspensions after last failure, then final TTT can be obtained using equation 8.26. If there is evidence that failure distribution is increasing failure rate class, then variable distribution can be assumed and the final term of TTT n plus 1 can be evaluated using the expression. TTT n plus 1 is equal to TTT n plus integral Tn up to infinity exponential minus T by alpha to the power of beta dt, where alpha scale and beta shape are parameters of variable distribution. The method of evaluation of second term in equation 8.31 is described in text section. The PEXE can be seen as a generalized of the Nelson estimator in its original form, that is without any suspensions. The PEXE is equal to the Nelson estimator. Precisely, survival function is Ri is equal to exponential bracket minus sigma I is equal to j is equal to I 1 to I 1 by n minus 1, and SI is equal to n minus sigma k is equal to 1 to I into n minus k plus 1 into tk minus 1 into rk minus 1 minus rk. The scaled TTT phi I is equal to Si by Sn plus 1, where Sn plus 1 is given by Sn plus 1 is equal to Sn plus alpha by beta into Tn by alpha into exponential minus Tn by alpha to the power of beta, and alpha and beta are ML estimates of variable distribution. MLE method. If the failure data is assumed to follow variable distribution and the ML estimates are known, then the failure rate is given by Ht is equal to beta by alpha into T by alpha to the power of beta minus 1, and the cumulative distribution function is given by Ft is equal to 1 minus exponential T by alpha to the power of beta. Identifying failure distribution and goodness of fit. We have already established methods for deriving reliability distributions directly from failure data through graphical models such as TTT plots. Now let us identify an appropriate theoretical distribution, perform a goodness of fit test and estimate the parameters through analytical models. In general, fitting a theoretical distribution is preferred to empirically developing a model. The reason for such preferences on fitting distribution and testing the goodness of fit can be estimated as A. Empirical model do not provide information beyond the range of the sample data. In reliability engineering, the tails of the distribution are of most interest to extrapolate to find trend, etc. B. A sample is only a small random subset of the population of the failure times, and it is the distribution from which the sample came but not the sample itself that is to be established. Thus, it is of the interest in determining the probabilistic nature of the underlying failure process. That is, generally the failure process is a result of some physical phenomena that can be associated with a particular distribution. For example, the central limit theorem provides justification for using the normal distribution when additive effects are present, or the log normal distribution when multiplicative effects are present. Chance or random process may generate an exponential time to failure. D. Small sample size provides very little information concerning the failure process. However, if the sample is consistent with a theoretical distribution, then much stronger results based on the properties of the theoretical distribution are possible. E. The theoretical reliability model can help in performing more complex analysis of the failure process. For example, the effect of change on the MTBF can easily be accomplished. Identifying candidate distributions. Identifying candidate distributions is both an art and a science. An understanding of the failure process, knowledge of the characteristics of the theoretical distributions, and a statistical analysis of the data will assist in selecting a failure or repair distribution. One suggested approach is given below. A. Construct a histogram of the failure or repair times, compute descriptive statistics, analyze the empirical failure rate, use prior knowledge of the failure process, use properties of the theoretical distributions, construct a probability plot, examine the goodness of fit. Goodness of fit test. Except for the final step in the above approach, all other steps are familiar to us. Hence, the final step in the selection of a theoretical distribution, that is to perform a statistical test for the goodness of fit, is explained here, such as test compress a null hypothesis H0 with an alternative hypothesis H1 or HA having the following form. H0, the failure times came from the specified distributions. H1 or HA, the failure times did not come from the specified distribution. The test consists of computing a statistics over a sample of failure times. This statistic is then compared with a critical value obtained from the relevant statistical tables. Generally, if test statistic is less than the critical value table value, the null hypothesis H0 is accepted. Otherwise, the alternative hypothesis H1 is accepted. The critical values depends on the level of significance of the test and the sample size. The level of significance is the probability of erroneously rejecting the null hypothesis in favor of the alternative hypothesis. Table 8.2 shows the 4 possible cases that may occur because of the randomness inherent in the sampling process. The test statistic has a probability of exceeding the critical value even though H0 is true. This result is a type 1 error having a probability of occurring equal to the level of significance, that is alpha. It is also possible for the test statistic to be less than the critical value even though H1 is true. This results in a type 2 error. It occurs with a probability that is usually controlled indirectly by the specification of the level of significance and the sample size. In this table you can see that decision table for hypothesis test occurrences. HA, if H0 is true, then accept HA, that is correct decision. Accept HA, that is a type 1 error. Then if occurrence is H1 is true, accept HA is the type 2 error, that is beta. Then accept HA, that is correct decision. So listen this table and read the table, then only you can able to understand correctly. There are two types of goodness of tests available. One is general test and another is specific test. A general test is applicable to fitting more than one theoretical distribution, and a specific test is tailored to a single distribution. If available, specific test will be more powerful, having a higher probability of correctly accepting or rejecting a distribution than general test. What follows is the discussion of the general test, the chi-square goodness of fit test, and specific test for the exponential, variable and normal and log normal distributions. Chi-square test goodness of fit test. This test is applicable to both continuous and discrete distributions and may be used when the parameters of the distribution are estimated from the maximum likelihood estimates. The test is valid for large sample size only. The data must be grouped into classes. Test statistic is chi-square is equal to sigma I is equal to 1 to k bracket OI minus EI whole square divided by EI, where k is equal to number of classes, OI is equal to observed number of failures or repairs in the ith class, EI is equal to NPI, that is equal to expected number of failures or repairs in the ith class, N is equal to total number at risk sample size, PI is equal to probability of a failure occurring in the ith class if H0 is true. The probabilities are passed on the distribution stated in the null hypothesis. To ensure an approximate chi-square distribution, NPI should be at least 5 for all I or use Sturges rule. The test statistics chi-square has a chi-square distribution with degree of freedom equal to k minus 1 minus number of estimated parameters. Critical values are then obtained from statistical tables. On comparison, if calculated value is less than the critical value, then we accept null hypothesis, otherwise we reject the hypothesis. So conclusions. Learners, I hope you understood the following: method of TTT plotting, concept of TTT transforms, different methods of constructing TTT plots, identifying failure distributions, goodness of fit tests, chi-square goodness of fit tests, etc. Thank you.